focus of our last two talks have been taking a function, f of x, and trying to represent it as an infinite polynomial. Exactly. So we picked the power series, which is an infinite polynomial. And this is the general form of a power series, where c sub n are just constants that depend on n, and a is the center. Thanks to Blake Taylor, he came up with a way of finding these c sub n's that would make it so that f of x would be completely represented by this polynomial. So what he did, we went through the proof. He proved that c sub n is the nth derivative at a divided by n factorial times x minus a to the nth. So this is known as a Taylor series, named after him. And the problem with the Taylor series is that it's got an infinite number of terms, so we never can really use all the terms. So in general, what we say is that f of x is, and we take the first term, well, the 0th factorial is really just the function. I mean, the 0th derivative is just the function divided by 0 factorial is 1, and x minus a to the 0 power is just 1. So usually the first term we just call f of a. And then we start going at n equals 1, and we get the first derivative divided by 1 factorial times x minus a to the first, and we keep going until we get to the nth derivative at a divided by n factorial times x minus a to the n. So we go up to x to the n power terms in our polynomial. And this is referred as Pn of x, an nth degree Taylor polynomial, plus what's left. And we call that the remainder, Rn of x. And it's going to be important to know what that remainder is, because that's going to say how accurate we're going to find our answer to be when we plug a value in for x and try to approximate f of x with this Taylor polynomial. You can kind of see there are two things that are going to affect this. One, all of these terms are going to have x minus a in them. So the smaller this is, the closer x is to a, the smaller the remainder is going to be, the smaller our error is going to be. So you want to pick a center close to the values of x that you're going to be plugging into the function. That'll lower the error. The other thing is, the less terms we have in our n of x, the less error there's going to be. So we want to take as many terms as we can in our Taylor polynomial. Now you might think that there's an infinite number of terms going to be left anyways, but what you see is all these terms are divided by n factorial, where n keeps getting bigger. So the terms themselves that you're leaving off keep getting smaller and smaller. So these beginning terms are going to be the more important terms. So the more of these that we can keep, the better. So our better approximation is more terms, bigger n, and also getting values of x close to a. Now, Taylor also came up with this Taylor remainder to be the n plus first derivative, but not at a, at c, divided by n plus 1 factorial times x minus a to the n plus 1. So they knew exactly how to find the remainder. The problem is, never do you know what C is. C is between A and X, the center and the value of X that you're plugging into the function. So that's kind of, when you put this and this together, this is Taylor's formula. So why don't we give one more example how to do this on a function. Now we've already done the sine of x, the cosine of x, e to the x, some of the ones that are the most important to represent as a polynomial. But I think if we just take the function 1 over x, there might be less use to have a Taylor series for it, but it's a good one to show how this is done. So, what do we need if we need a Taylor series? We need the function value and we need a bunch of derivatives. So, the third derivative, the fourth derivative, so f of x is 1 over x. The derivative, the second derivative, the third derivative, and the fourth derivative, which you can write maybe without the negative exponents, 2 over x cubed, negative 6 over x to the fourth, and 24 over x to the fifth. And from our formula, we see we now have to plug in to the function value and to the derivatives the value a. So what we're going to do in this one is we're going to look for values of x to plug into 1 over x that are close to 2. So we're going to let 2 be the center. So that means f of 2 is 1/2. F prime of 2 is negative 1 over 2 squared. F double prime of 2 is going to be 2 over 2 cubed. And then the third derivative is negative 6. But I'm going to call that negative 3 factorial over 2 to the fourth. And the fourth derivative is 24, but that's 4 factorial over 2 to the fifth. And I could call 2 factorial and 1 factorial. So now when I go to use Taylor's formula, I say f of x equals, and now I say the first term is f of 2, 1/2, plus f prime of 2 over 1 factorial times x minus the center 2 to the first power. Then you go plus the second derivative, 2 factorial over 2 cubed, all over 2 factorial times x minus 2 squared. Then you go to the third. So we go minus 3 factorial over 2 to the fourth, all divided by now 3 factorial, all from the formula, times x minus 2 cubed, and then the last term, you're plus 4 factorial over 2 to the fifth, divided by 4 factorial, times x minus 2 to the fourth. And this is approximately equal to, because we're only doing a 4th degree Taylor polynomial. Now let's see if we can simplify this. 2 factorial divided by 2 factorial. 3 factorial divided by 3 factorial. All those factorials cancel out. So we're left with 1/2, then minus 1 over 2 squared times x minus 2 to the first. Then we have plus 1 over 2 cubed times x minus 2 squared, then minus 1 over 2 to the fourth times x minus 2 cubed, and lastly plus 1 over 2 to the fifth times x minus 2 to the fourth. And we see a pattern. So I could actually write this as a summation. And I'll start at n equals 1 to infinity. Now it's going to be exactly, because I'm going to write it as a summation. So what do I see? It's alternating. So I go negative 1 to the n, but when n is 1, I want it to be negative. So I put to the n plus 1 power. And then I'm dividing by 2 to a power that's always 1 bigger than the term. So this has got to be to the n plus 1. And then you're multiplying by x minus 2 to just the n. So if you wanted to check it, try it when n is 2. You get x minus 2 squared. You get 2 to the third power. And when you put in n equals 2 here, you get negative 1 cubed. So maybe I've got that wrong. When n is 1, you want it to be odd. So we do want to leave it with just n. So it's always good to check it like that. So anyway, now this is not a Taylor polynomial. This is a Taylor series. But if we actually wanted to plug a value in there, we can never do the infinite amount. So say, for instance, we wanted to put in some values. But first of all, you have to find out where this series converges. Because if it doesn't converge, you can't really use it for a value of x. So now we're going to go to the ratio test. So we take the limit as n approaches infinity, but the ratio test only works on positive terms. And some of these terms, depending on what x is, might be negative. So we do it on the absolute value. So if I take the n plus first term, and since I'm doing absolute value, I can not worry about the negative sign. So I get x minus 2 to the n plus 1 over 2 to the n plus 2. And then I have to divide it by the nth term, or multiply by the reciprocal. So 2 to the n plus 1 over x minus 2 to the n. So since we're using the absolute value, this is going to show where it converges absolutely. So we can do some simplification. 2 to the n plus 1 over 2 to the n plus 2 is 1/2. X minus 2 to the n plus 1 over x minus 2 to the n is just x minus 2, and it's still in the absolute value. And all we have left, there's nothing left. It's just the limit as n approaches infinity of 1, which is just 1. So that's all we get for rho. And we know by the ratio test, this converges when this is less than 1. Or basically, when x minus 2 in absolute value is less than 2, or x has to be between 0 and 4. And we know, because it was proven, that it diverges everywhere else, that it doesn't converge absolutely, except possibly at the endpoints. So we have to go back to this and try n equals 0 and n equals 4. Well, when we put in 0, well, when we put in 4, I mean, we get 4 minus 2 to the n. 2 to the n over 2 to the n plus 1 is just 1/2. So that would be what you'd be adding up. Well, those terms don't go to 0. So 4 doesn't work. We don't want to have an equal sign. And when we put in n equals 0, we get -1 to the n. Now we get -2 to the n, divided by 2 to the n plus 1, which is just -1 to the n over 2. So again, we get terms that don't add up to 0. As n approaches infinity, these terms don't approach 0. So neither of the endpoints work. So this is the interval of convergence. This would be called the radius of convergence because it goes 2 on each side of the center. So I only can plug values of x between 0 and 4 in to get any answer that makes sense, that converges. So let's try it on one value. Let's try it on x equals 3. So if I plug 3, and we're going to plug it right into here, I plug 3 in, I'm going to be approximating 1/3. So 1/3 is approximately, and the first term is 1/2 minus 1/4 times 3 minus 2, because you're putting 3 in for x. So that's just going to be, I'll just write it in there, to the first power, plus 1/8 times 3 minus 2 squared, and then minus 1/16 times 3 minus 2 cubed. So say we stop there. We're saying 1/3 is approximately 1/2 minus 1/4 plus 1/8 minus 1/16, which if you add them all up, it's approximately 5/16. And then, what about the error? Well, let's practice this error. That's the remainder right there. So we know the remainder is going to be f of, and we've used up to how many terms? We've used up to cube terms. So we're going to go to the 4th derivative at where? At c over 4 factorial times x minus a. Well, that's 3 minus 2 to the 4th power. And what do we know about c? c is between a and x. c is between 2 and 3. And we're never going to know what c is. This is the exact error, but we don't know what c is. So all we can do is give an error bound. And we usually do it by the magnitude of the error. And this is called the Lagrange Airbound. And what it is, we can say the error is less than, and we pick 4 factorial times 1. What is the 4th derivative? Well, the 4th derivative is right here, 24 over x to the 5th. But we're going to put the biggest value this could possibly be. It's 24 over c to the 5th. Well, what's the biggest 24 over c to the 5th can be between 2 and 3? It's trying to get the smallest denominator possible to get the biggest number. So if we pick 2, now we know the error is less than that. You could put an absolute value, but I see everything is positive there. The 24s cancel out, and I get 2 to the 5th. So what we've done is we've shown that the error is less than 1/32, approximately 0.03. So that's a pretty good bound, because we know our answer isn't too bad. Now to actually check it, 1/3 is 0.333 5/16 is 0.315, you get 0.02 about. So the actual error is about 0.02. Your airbound said it's less than 0.03. So it did a pretty darn good job. Now I wanted to practice the Lagrange Airbound. We actually could have done this one because it's an alternating series. We could have just said the error is less than the first term we omit. Right there, using the alternating series estimation theorem, that's easier than doing this. And you see you get the same thing. If you put a 3 in here, you get 1/2⁵. But if you don't have an alternating series, you have to use the Lagrange Airbound rather than the alternating series test bound. Okay, so that's quite a bit of work, but it's really comprehensive. And it shows you all the steps you have to go through. Now, do you always have to do that? No. If you already have a series that you can start with, then you can save yourself a lot of time. Like the tangent of x happens to be represented by this Taylor series. It's a very complicated one to figure out. But say you really wanted to know a series for secant squared of x. Well, since you know that the derivative of the tangent is the secant squared, all I have to do is take the derivative. 1 plus x squared plus 2/3 x to the 4th, and then plus 17 times 7 x to the 6th over 315. It's that simple to go from one to the other. And we practiced some of those in the last couple talks where we take derivatives or we take antiderivatives or we plug 2x in for x or x squared in for x. So anyway, this is how you do Taylor series. So now what we're going to do is kind of end up this chapter with just a couple of examples. First of all, I picked an example more difficult than you're probably going to have to deal with, but this is if you were taking higher physics and studying quantum mechanics. In studying the hydrogen atom in quantum mechanics, the Legendre differential equation arises. And it's a second order. It means it's got a y double prime in it, differential equation, and it's not easy to solve. Even if you took Calculus 4 in college, called differential equations, it's still a very difficult one to solve. But say you wanted to get a solution to it, and you're okay with just an approximate solution. What could we do? We could take a polynomial. We could take a Taylor series for the value of y. So what would a Taylor series look like? You would say y of x is approximately equal to y of a. Well, we can pick whatever a we want in this case, and look at it. We already know what y of 1/2 is and what y double prime of 1/2 is. So let's pick our center to be a. Plus y, now we just write the formula. Over 1 factorial times x minus a to the first. Plus y double prime over 2 factorial times x minus 1/2 squared. And I was just going to do a second order, but I thought, this is the last day. Let's really go for it and do a third order. So we have to go up to x cubed terms. So we need the third derivative divided by 3 factorial. And if we could get that, that would be a third order Taylor polynomial that would be an approximation to the solution. And maybe that's something that we could use. So what do we need? We've got everything in here except the second derivative and the third derivative. We already have these two. So we can say that y of x And right away, y of 1/2 is 2. Y prime of 1/2 is 3. Now we have to get y double prime. Well, what do we have on here that's going to get us y double prime? We've got this differential equation. So we should be able to plug in any value of x and y. So let's plug in 1/2 for x and 2 for y. So we get 1 minus 1/4 y double prime minus 2 times x times y prime. Y prime at 1/2 is 3 plus 12 y, and y is 2, equals 0. So altogether, 3/4 y prime equals 21. So y prime must be negative 21 times 4/3, or negative 28. Sorry, y double prime. That's what we're solving for. Now we've got y double prime. It's negative 28. So this makes this negative 28 over 2 factorial. And we only have one more thing to get. We need the third derivative. Well, you can't get the third derivative from here, but we could take the derivative of this implicitly. So let's do it. We have to do the product rule. 1 minus x squared times the derivative of y double prime, which is y triple prime, plus y double prime times negative 2x, minus 2, now times the derivative of xy prime. The first times the derivative of y prime, which is y double prime, plus y prime times the derivative of x, which is 1, plus 12 times the derivative of y equals 0. And we want to solve for y triple prime. We put in x to be 1/2. So we get 3/4 y triple prime plus y double prime, which is negative 28, times negative 2x, which is negative 1. X is 1/2. Y double prime is negative 28. And y prime is 3. And then 12 times y prime equals 0. So 3/4 y triple prime equals, well, that's 28 plus 22 plus 36. So that means y triple prime is 86 times 4 over 3, or 344/3. So I can now get my last term. 344/3 divided by 3 factorial times x minus 1/2 cubed. And now we've got something that we can use to help study the hydrogen atom in quantum mechanics. So that's pretty exciting. So as long as we're doing exciting things, this is something that we should do sometime this year. So why not now? This is the first time now that you can really understand it. So let's take e to the x, which now we should have memorized. 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial, and it keeps going. Let's plug in to x e to the I pi. And what do we get? 1 plus I pi plus I pi squared over 2 factorial plus I pi cubed over 3 factorial plus I pi to the 4th over 4 factorial plus I pi to the 5th over 5 factorial plus forever. Now, let's see if we can simplify things. And at the same time, let's do it every other term. So we're going to take this term plus this term plus this term. So you're starting out with 1 plus, well, I squared is negative 1. So this is actually minus pi squared over 2 factorial. And then this term, I to the 4th, is equal to 1. So we have plus pi to the 4th over 4 factorial. And it keeps going. So we have that. Now, let's look at the other terms. You have I pi, and then you have I cubed. Well, I cubed is negative I pi cubed over 3 factorial. And then you get I to the 5th. Well, that's back to just I again. So you have I pi to the 5th over 5 factorial. And then it keeps going. Well, I can factor out an I. And what do I get? Pi minus pi cubed over 3 factorial plus pi to the 5th over 5 factorial. And I'm almost there. When we look at this series, doesn't it look a lot like the cosine? This is a Taylor series for the cosine. In place of x, we plugged in pi. So this is really just the cosine of pi plus I. And if you look at this series, it looks like the sine Taylor series with pi plugged in for x. So this is the sine of pi, which is negative 1 plus I times 0. So what do we have? E to the I pi plus 1 equals 0. We have Euler's equation. Very famous. Why is it so famous? It shows the 5 most important numbers in all of mathematics in one simple little equation. So this is something, if you're not feeling quite as good as you'd like to, and you wonder about the nature of things, just say the universe is in good shape because this still holds. So prove it to yourself if you ever feel that way. Okay, so that pretty much ends the chapter. But I think what we're going to do is end this chapter with a song. And sorry, I don't sing very well. And I didn't write this myself. I borrowed it from another teacher. But I think it really sums up this whole chapter. So I hope you know the song Home on the Range. Oh, give me a home where derivatives roam and factorials frolic and play, where a small airbound is quite easily found if your center's not too far away. Home, home on Lagrange, as Maclaurin and Taylor would say. If your numbers aren't firm, just keep adding a term, and the errors get smaller all day.